So this question is from GATE examination of 2023, and this is a numerical type question, and the question states two identical non-interacting 4 helium atoms are distributed among 4 different non-degenerate energy levels. The probability that they occupy different energy levels is P. Similarly, two free helium atoms are distributed among 4 different non-degenerate energy levels, and the probability that they occupy different levels is Q. So, what is the value of P upon Q? And this should be rounded off to 1 decimal place. Now, in order to solve this, first I need to clarify a little concept upon regarding to the or bosons and fermions. So we know that an atom can be called as boson or fermion depending upon the number of its constituents, or the constituents are, that is namely protons, neutrons, and electrons. So in short, I can say if N plus P plus E, where N is the neutron number of neutrons, P is the number of protons, and E is the number of electrons, is even, then the atom is a boson. And if N plus P plus E is odd, then the atom is a fermion. Okay, so this is a little concept I am going to use. So let me write, instead of P here, let me write PR, because in the question it is given as P. Okay, so for helium 4, proton number is 2, so our neutron number is 4 minus 2, that is also 2. Our electron number is equals to the number of protons, that is also 2. So here proton plus neutron plus electron equals to 2 plus 2 plus 2 equals to 6. So 4 helium is a boson. Okay, and two, for this case proton number is still 2, but the neutron number is 3 minus 2, which is 1, and number of electrons is equals to number of protons equals to 2. So in this case, protons plus neutron plus electron makes up as 5, and that means 3 helium is a fermion. Okay, now again let us go back to the question. So here state that these atoms are to be distributed among 4 different non-degenerate energy levels. Okay, so let me start with the case 1. Distribution of 2 atoms in 4 non-degenerate energy levels. Okay, so here we have 4 energy levels: 1, 2, 3, 4. Let me call it as small a, small b, small c, small d. Now, as these atoms are bosons, let let me define, let me denote for helium as A. So, as they are bosons, so I can place both the atoms in a same state, and this can be done in 4 ways, like this, this, and this. So the partitions are actually so different states. Okay. Now two atoms can lie in two different states. Okay. So let me first think. One atom is at state D. The second atom can be in state C. So this is a possibility. And the second possibility comes one atom at state D and the second atom is at state B. Now here again one atom at state D, one atom at state A. Now I can put one atom at state C and one atom at state D. Okay. Again one atom at state C and one atom at state A. And finally I can put one atom at state A and one atom at state B. So these are all the possibilities in which these atoms can be arranged. Okay. So here I have total. So total number of arrangements equals to 10. Okay. So four arrangements where both the atoms are in a same state, and 6 arrangements where both the atoms are in different states. Now what is being asked? So the probability here, the probability that they occupy different energy levels. Okay. So uh, total here arrangements where they occupy different states is 6. So the probability, which is defined as small p, equals to 6 upon 10, and this gives me 0.6. Okay. Now in case 2, it is for distribution of two 382 atoms in 4 non-degenerate energy level. Okay. Now, as I have said earlier, that 382 is a fermionic atom, so this must obey Pauli exclusion principle, right? And let me define 382 as B. So as they obey Pauli exclusion principle, so two of the atoms cannot lie in the same energy level. So here both of them should lie in different energy levels. So just like in the previous case, let me just draw four energy levels and name them as A, B, C, D. So here for the first case, both the atoms can lie in states A and state B respectively. The second case, they can lie in state A and state C. Third case, state A and state D. And then obviously state B and state C, then states D and states D, and for the final case, it should be in state C and D. So here, total number of arrangements equals 6. Total means in which the atoms stay in different states is also 6, so that Q is 6 upon 6, which is 1. Now we need to find the fraction P upon Q. And P is already we have found as 0.6 and Q as 1. So P upon Q is 0.6. So this is the answer to this question.